Athanasios, you can start.
Thank you, Dimitris. And it's well, it's really nice that I am the one giving the closing talk for this seminar, and I look forward for next semester as well as a participant. And so today it's the second part of my talk. I started last Monday, and I did a historical survey beginning from Riemann's memoir about the value distribution of the Riemann zeta-function, and then we end up with Voronin's theorem, which I also give a small recap here to remind it. So we have a compact set in the vertical strip of complex numbers with real part between 1/2 and 1, and we have an arbitrary target function f defined on the set K, which is continuous on the set and analytic in its interior. Then for every error, epsilon, there is a vertical shift of the Riemann zeta-function such that its image over the set K is close to f. And because f, the only problem with f is that I probably haven't written it here because I forgot, but f is also not allowed to have zeros. So it's also a non-vanishing function on the set K. And because the Riemann zeta-function approximates a wide class of analytic functions, except of the ones that may have zeros, we say that this is a universality theorem, and the zeta function is a universal vector in a certain space. And the proof actually of Voronin, he wrote it like this, but it's implicit in the proof that the proportion of those real numbers tau, these translations or shifts as you prefer, it's this positive in the sense that this limiting minimum of 1/t, the Lebesgue measure of such tau that the above inequality holds, is a positive number. And we call this set a set of positive lower density. We will come again to this. And before I want to show more examples of zeta functions having the same property, this star property as the Riemann function. I want to say something about direct applications of universality, which since if you can prove it for I want to show them for the Riemann function, but they apply for any other zeta function or any function have this property. So this just in this case just the Riemann function is the model. So it was already done in the 1980s that the Riemann hypothesis is equivalent to the statement that the Riemann function approximates itself in the sense of Voronin with the positive lower density property. And this is immediate to see. So if the Riemann hypothesis is true, the Riemann function has no zeros in strip 1/2, 1, and thus it belongs to the class of functions that can be approximated by the Riemann function shifted by I tau. And the converse is by contradiction, assuming that this inequality holds for a positive proportion of tau, and there is a zero of the critical line. It was like we did last time with Bohr's argument. Then this would imply a positive proportion of zeros of the Riemann function of the critical line, which would contradict zero density estimates, which we know that they imply that if there are zeros of the critical line, there are not too many. And towards this statement, which is equivalent to the Riemann hypothesis, there has been some progress, which of course is still elusive. In the case that if you have a real number d, then the Riemann function, as you shift it by I tau, and simultaneously as you shift it by I d tau, they can be arbitrarily close for a positive proportion of times. And d can be any number, but of course it can. Of course, it has not been proved, and probably it's very difficult to prove that this can hold for d equal to 0, right? Because it's equivalent to the Riemann hypothesis. Now, a second consequence of the universality is with respect. It's actually with respect to what functions what target functions you can approximate. As I said, they can be only non-vanishing. They cannot have zeros. And that is also, it's a necessary condition, because if the Riemann function could approximate a function with a zero, then the positive density proportion, the positive density of the shift tau would again imply by Roussier's theorem too many zeros of the critical line, a contradiction. But it's quite interesting that if you could have this inequality, this approximation without the positive density, so for a sparse set of shifts tau, This would give some zeros, not too many, and you would disprove the Riemann hypothesis without contradicting zero density estimates. However, this any such proof would not follow from the tools that have been developed for the universality theorem, because all these tools are characterized by proving some positive denseness in a certain sense in the real line. So some other techniques would have to be developed to show something like this without the positive denseness. Now, another consequence is with respect to the multidimensional curve of the consisting by the Riemann zeta-function and its derivatives. So you fix a complex number, a real number sigma between 1/2 and 1, and then you can show that this curve is dense in Cn plus 1. And the proof with using the universality theorem is really 4 lines. You take an arbitrary vector with a non-zero first coordinate. You construct an analytic function in a sufficiently small disk around sigma, whose first Taylor coefficients are given by these coordinates of the vector. You use the universality theorem to approximate your target function z, which is not zero for a sufficiently small disk because the first Taylor coefficient is not zero. And then by Cauchy estimates, you just show that the Taylor coefficients of the first Taylor coefficients of the Riemann zeta-function in this disk is close to the first Taylor coefficients of this function g, which are of course the coordinates of the vector you want to approximate. But the universality theorem can even tell you much more about this denseness of the curve zeta sigma plus I tau. So in general, we first use the observation of Anderson, who showed that if K in the theorem of Voronin has empty interior, then there is no sense to talk about analyticity, right? The target function can be only continuous because the interior is empty. But it can also have zeros. So, and still, you can approximate this function with the Riemann zeta-function without contradicting anything, for obvious reasons. The analyticity is a major part in the contradiction. And then we know already from Bohr, but also from the universality theorem, that this spiral, you have a vertical line sigma plus I tau, and then you map it with the Riemann zeta-function. It looks like a spiral. It starts from the negative axis, and then it looks like it's doing these turns on the left side. The universality theorem basically says us that these spirals actually, in the long run, can approximate any continuous function from R to C, actually from an interval of R to C. So in this case, in this example, I just have a circle in yellow, and then you can see that after some time, the spiral will look like it would be close to circle up to an error epsilon. If you want smaller epsilon, you have to go higher, and this spiral eventually will look like the circle. You cannot distinguish with a naked eye. But the universality theorem also says something else. I just said you can approximate any continuous function, any curve, any plane curve. So the spiral can also look like this. Now, of course, if you plot the Riemann zeta-function with the power that computers have right now, you will only see sketches like this, like spirals. But the universality theorem says that at some point, at some height, which we cannot find effectively, the curve will look like this, which is not a spiral anymore. Okay. So another consequence of universality is with respect to algebraic differential equations. So we say that the function f from C to the extended complex plane is called hypertranscendental. For those who are Greek, you can translate this, and it's quite amusing, the translation. So we say that such a function is hypertranscendental if it does not satisfy any algebraic differential equation. In the sense, you have a polynomial of a multivariable polynomial, and it's the non-zero polynomial. Then there will be a complex number such that this relation is non-zero. And it was already known in the 19th century, in the beginning, that the Riemann zeta-function is hypertranscendental. This has been observed by Hilbert first, using the hypertranscendence of the gamma function, which was known by Holder. And then Stadig proved it in his thesis, and then Ostrovsky generalized it to more arbitrary Dirichlet series, because the Riemann zeta-function is a Dirichlet series. And recently, like in the 80s, many decades later, Reich could improve this result by substituting the polynomial by something more general, in this case, a holomorphic and not identically vanishing function, a multivariable function. And however, the universality theorem implies even something much stronger. You can have a collection of continuous functions, not identically all vanishing, phi1, phi2, phi1, phi2, phi m. And then you can show that if not all of them are identically vanishing, then there will be a complex number such that this expression is non-zero. And we talk about this is, of course, it's a general version of the hypertranscendence, and we call it functional independence. So universal zeta functions and L functions are also functionally independent. You should not expect them to be solutions of any differential equation or algebraic differential equation. Now, coming to examples of universal zeta functions, the first one is with respect to L functions or zeta functions which have an Euler product, right? Like the Riemann zeta function. So you have an L function which can be written as a Dirichlet series, and the coefficient an is an arithmetical function which is multiplicative. Multiplicative is this property that I write in the first line, that a of m times n is am times an for all coprime integers m and n. GCD means the greatest common divisor. And if you can omit this condition of the greatest common divisor, then you say that the term is completely multiplicative. Anyway, just with multiplicativity, we can deconstruct this series using the geometric series as a product of geometric series, as we did for the Riemann zeta function. And this is a Dirichlet series, and this is an Euler product of smaller geometric series. And the absolute convergence doesn't need to be at 1, as it was for the Riemann zeta function, but it will be greater, on some real number greater than sigma 0. And this depends on the growth conditions of the coefficients an. In the Riemann zeta function, it's just 1, so it's really bounded that you can control it. Now, and to prove universality, we need to, as in the Riemann zeta function, we need to consider the finite Euler product. Here, the primes are up to some threshold m, and the twisted Euler product, where we have the same expression, only this time we are multiplying with some vectors from the unit circle. And the 3 steps of universality is first to show that the logarithm of this set of logarithms of twisted finite Euler products is dense in a certain space of analytic functions of some vertical strip, not 1/2 but some vertical strip. And then to show that the logarithm of the finite Euler product on the left is close to the logarithm of the twisted one for a positive proportion of real numbers tau. And the 3rd step is to show that these logarithms of the same finite Euler products are close to the logarithm of the original function, the L function, with high probability, meaning that if you have more terms in the Euler product, as n goes to infinity, you have more primes here to consist your finite Euler product. This will have a higher probability going to 1 of being close to the logarithm of the L function. So if you have these 3 steps, you can prove universality. And actually, why do we use the logarithm? We use the logarithm because the integers are not multiplicative independent. They can be decomposed in smaller blocks, the primes. So the logarithm can take us from the construction of integers here to the construction of primes, which are behaving more independently. And doing these steps, actually, we can show that the logarithm of the L function we are considering is close to a target function which can also have zeros on a compact set K. So it has a stronger version. However, when we want to go back to the original L function, we have to exponentiate. And then the target function becomes exponential of the target function, and then you lose all zeros that could have been there. That's why the target function cannot have zeros. So the model for the first model for these functions with an Euler product are excluded the Riemann zeta function are the Dirichlet functions. So you have an arithmetical function from n to the unit circle and the 0, the center, and it's a multiplicative q-periodic function such that it's 0 if and only if the integer n is not coprime to q. In all other cases, you are around the unit circle. And then you have the associated Dirichlet function, which can be written as a Dirichlet series. And because your function is completely multiplicative, it can be deconstructed as an Euler product. This has been introduced actually by Dirichlet to prove that there are infinitely many primes in arithmetic progressions. He couldn't prove the prime number theorem, like how regular you can find primes in arithmetic progressions, but he could prove that there are infinitely many. And it was done recently, not recently, shortly after Voronin's proof, that also the Dirichlet functions are universal in the sense of Voronin. This has been done by Bakhtchi, Gonek, and Voronin independently, different countries, far away. Maybe the internet was not a thing then, and they proved it. And the key ingredient for the proof was the prime number theorem for arithmetic progression. There are regular primes inside the progression. And another generalization is with respect to modular forms. As I said before, Dirichlet functions are constructed by periodic functions which are multiplicative. And in a sense, modular forms are the same thing, are multiplicative functions which are periodic in the upper half plane. So you have a holomorphic function which is defined in the upper half plane like this, and it's called a cusp form if when you take a matrix from to Z, this is the set of, let's say the set of 2 by 2 matrices with integer coefficients and determinant 1. You take a matrix like this, and then you act in the sense of Moebius transformation on a complex number of the upper half plane. You take this expression here, which is the Moebius transformation, and the function f should map it to the original number z, f of z, times a certain weight, which is given by the integer c and d. And the weight k that's why we call it a cusp form of weight k. Now, it also, this modular form should also vanish to the cusp. When I say cusp, I mean to I infinity, and this is equivalent to saying that this function is bounded on the upper half plane. And because it's periodic, it has a Fourier expansion. It can be written like this for every complex number in the upper half plane. Then we pick the Fourier coefficients of this Fourier series, and we construct the associated L function of this modular form. And this is absolutely convergent, not for complex numbers with real part greater than 1, but greater than kappa, k plus 1 over 2. And this depends on the weight of the function of the modular form f. Now, this has also been proved that it has all the right things that we want, periodicity and multiplicativity, and it has been proved that it's universal in the sense of Voronin in the strip k over 2 and of complex numbers between k over 2 and k plus 1 over 2. And the key tools for the proof is the Linus bound for the Fourier coefficients, that they do not grow too fast. And in this case, you have this inequality that Cn are just bound by n, the weight k minus 1, and times d of n. And d of n counts the prime, it's the divisor function, which counts the divisors of an integer n. And lastly, you need also a prime number theorem for the Fourier coefficients, that we don't know whether these Cn's, how much they vanish and how often they vanish. And this is also a very challenging problem in analytic number theory to find out how they behave, this coefficient Cn. But these prime number theorems give us enough information on the non-vanishing of these coefficients on the primes and how regular these coefficients are and how they grow. All right. And another example, coming mostly, I think, from algebraic number fields, is the Dedekind zeta-function. Now you have an algebraic number field, which is just an extension of Q by embedding some algebraic number like Q square root 2, and you have its degree D. Then the Dedekind zeta-function is defined as a Dirichlet series again, where the sum is taken over all non-zero integral ideals of the ring of integers of your field, and n here is the norm of the ideal. This is also a multiplicative arithmetical function, as defined like here. You can decompose it as an Euler product over the prime ideals of your ring of integers. It can be absolutely convergent. This series can be now absolutely convergent, is absolutely convergent for real part of s greater than 1. And some known facts from the early 18th and 19th century. It's, of course, the class number formula. This was done by Dirichlet for quadratic number fields, and this has been generalized by Hecke. So you know that the pole of the Dedekind zeta function at s equal to 1 gives you information about the class number of your field, which counts the deviation of its field of being of the class number of the ring of integers, which counts the deviation of the ring being having unique prime factorization. Some of them don't. And also, we have a prime number theorem for the prime ideals of the ring of integers, which was proven by Landau, which the proof is similar to the prime number theorem for the Riemann zeta function. Anyway, using those two facts, again, you can show that the Dedekind zeta function is universal in the sense of Voronin, but not anymore in the strip 1/2, but in a thinner strip that it depends on the degree of the extension field of K, of the algebraic field K. You see that if higher the degree, you have to go closer and closer. And this is a problem that arises from the third step, when you want to approximate the Dedekind zeta function by a finite Euler product. You don't have a good mean square approximation for it. And we pass now to zeta functions which do not have an Euler product. In this case, you just have you can write as a general Dirichlet series. This is an infinite series with some coefficients a and complex, which are also non-zero. That's can assume without loss of generality, and it converges absolutely in some half plane greater than sigma 0. And the frequencies here are lambda n, and they should tend, well, in this case, not necessarily to plus infinity, but to make our life easier, let's say that they will tend to plus infinity. Now, in this case, we don't have a decomposition in primes, right? Not necessarily. We have to say that we say that this function does not have an Euler product, so we don't have such a decomposition, and then we have to work directly with the Dirichlet series and not with an Euler product. Namely, we have to take a finite expression of this series, which we call it the finite Dirichlet series, up to some threshold m, and the twist of it. So you just multiply some complex numbers from the unit circle. And then you just need to prove the universality similarly. So you show that not the logarithms, but the twisted finite Dirichlet series is dense in some certain space. Then you need to show that the finite series is close to the twisted one for a positive proportion of tau. And then you need to show that those finite series, those finite Dirichlet series are close to your original series, your original L function, sorry, with high probability. And doing all these steps, we can actually show that the L function, as I said for the logarithm of the zeta function, it approximates also functions with zero. And that's why we call it strong universality, because it approximates even more functions than the Riemann zeta function, which approximates only functions without zeros. And classical, and to achieve this, to achieve this universality, you still need something like a prime number theorem, only this time for the frequencies that are involved in the Dirichlet series decomposition of your L function, so that this counting function weighted by the coefficients of the Dirichlet series grow moderately, not too fast and not too slow. And also that these frequencies, like the logarithms of the primes, in the case of the Riemann zeta functions, are linearly dependent over the rationals. This means that if you have a linear combination of them for some integers kn, any collection of them, if such an expression is zero, this should imply that all integers in this expression are zero. Namely, you don't have a non-trivial relation between them. So if you have these two conditions, most of the times you have to prove these conditions, then we can show that the L function without the Euler product can approximate a target function without zeros, and that's why we call it strong universal. Exactly. So a first example, which is the straightforward example, to take the simplest one, is the Hurwitz zeta function. Here we have that an, the coefficients in the Dirichlet series is just 1, and the frequencies, they look like the Riemann zeta functions, but instead of having n to the s, you have n to n plus alpha to the s. And alpha is some parameter which we fix, and it's from the unit interval. Now, in this case, the frequencies are the logarithms of n plus alpha, and the counting function is the integer part of x when the magnitude is x. We also want some linear independence over these frequencies, which means that assuming that there was some non-trivial linear relation between them, something like this, then using properties of logarithms, of course, you can group them together and you can show that the logarithm of the product of this expression, here we just take n plus alpha to the power of kn for those integers kn which are positive, should be equal to the not the logarithm, but this product should be equal to the product of the same n plus, not the same n plus alpha, but those n plus alpha which are in the power of minus kn for negative kn. And when you open the products, you get a polynomial of integer coefficients. Thus, this happens only when your parameter alpha is an algebraic number, a solution of a polynomial with integer coefficients. So if we take a parameter alpha to be a transcendental number, then all the conditions that I told you before are satisfied. And this has been done already by Gonick in the late 70s to show that the Hurwitz function is strongly universal in the strip 1/1. And this can now we can generalize this even more. Instead of having 1 in the coefficient of the Dirichlet series, you can have also numbers from the unit circle. In this case, we talk about the Lerch zeta function. So it's defined similarly as for the Hurwitz function, only this time we also have some certain twists. And the proof doesn't change, actually. You can show that it's strongly universal when the parameter alpha is transcendental. And what happens when alpha is not so transcendental? So what happens, it can be a rational number or an algebraic number. So if it's a rational number, actually, there is a certain relation between the Hurwitz function and Dirichlet functions. You can write it as a linear combination of Dirichlet functions as I defined them before. And if one could show that each Dirichlet function from this linear combination with some exponential function here, q is not important because it's periodic. So it always comes back to certain functions. So if we could show that each term of this sum is close to a target function multiplied by these factors here, phi q here is the Euler-Toshin function, which counts the number of integers which are coprime to q. Q is an integer. And if we could do this simultaneously, then the whole sum should approximate this sum of f of s of chi a phi q f of s, which would give you phi of s. And this would give you the approximation of phi of f of s by the Hurwitz function with rational parameter. And this is known now. It's called now this simultaneous approximation is called joint universality, and I will talk about it shortly after. The question about algebraic number alpha still remains open because when your parameter alpha is algebraic, you don't have linear independence of the logarithms of n plus alpha as in the case of transcendental numbers. And you also don't have an expression as a linear combination of other functions that you know, as in the case of rationals. There has been some work by Misu where he uses some theory from algebraic number fields, and I have also done something with Jorn Stoeding, but still not a closed thing. We have proved universality theorem for algebraic integer parameter alpha, but not for all of them. We had to exclude a finite set of them, and there's still some remaining cases that have to be considered. Now, as I said about joint universality, it's a kind of universality, and the universality of Voronin it can be called continuous universality, or the simplest case of continuous universality. So we have the joint universality, which is the first one was with respect to Dirichlet functions, and to have joint universality, you need some sort of independence. So we have we say that the principal Dirichlet character modulo q is just the character that takes the value 1 at coprime integers to the integer q and 0 at all other integers. And a Dirichlet character is called imprimitive if there is a prime, if there is a divisor of your modulus q such that this character can be written as the primitive character modulo q times this smaller character modulo r. And this character, chi, then is called, it's said that is induced from chi1. Now, two characters are equivalent if they're reduced by the same character. And if they are not, then they're called inequivalent. And we need this kind of inequivalence to prove this joint universality theorem for Dirichlet functions. And this was done again by Batzigonek and Voron independently. You have a collection of Dirichlet characters which are inequivalent pairwise. And then you have also a collection of compact sets with connected complement and functions which are analytic and continuous analytic in the interior of each of these sets and non-zero. Then the number of numbers tau shifts such that simultaneously all Dirichlet functions from this family are close to its target function has positive lower density. And this is how the joint universality theorems look like. So what you need is basically that because the characters are inequivalent, you need this formula from algebra also, right? I mean, that the sum of characters, when you sum them up over all residue classes modulo q, will be equal to phi of q only when you have the sum is over the principal character and zero otherwise. There is some sort of orthogonality. So you can generalize this to a certain sense. So you can have a collection of L functions which can be written as they have a certain Euler product. That means that the coefficients AIN are multiplicative or even completely multiplicative. And you need some sort of orthogonality, like for the characters, on the primes. And the first thing shows that you have a prime number theorem, namely that the coefficients of this Dirichlet series do not vanish, but they are appearing regularly over the primes. But also you have this orthogonality, namely that this quantity is not big, it's bounded. Even zero, if you could prove it's zero, it's even better. When you have coefficients from different L functions. So if you could prove this, then most likely you can prove that this collection of L functions, and in the Dirichlet function case works, they're also jointly universal. And for an example of strongly jointly universal, we can use this. It's actually even easier to check Lerch zeta-functions or Hurwitz zeta-functions, where the parameter alpha in the denominator, where we had n plus alpha, for each of them are transcendental numbers which are algebraically independent between them, because it could happen that one of them is E and the other one is 2E. And then you don't have algebraic independence, of course. Having this condition, this algebraic dependence, would give you also that this collection is jointly strongly universal because you can approximate also functions with zeros. Now, another type of universality, also quite popular, is the discrete universality. In the case of Voronin, we said that there is some real numbers tau, a positive proportion of them, such that you have this approximation. But the theorem of Voronin does not give us any information on how these real numbers tau may look like. It can be integers, it can be from arithmetic progression, can be squares or cubes. We don't know. And the first result towards this direction was by Reich in the 80s. So you have the same conditions as in Voronin. Only this time you can prove that the Riemann zeta-function approximates a target function through an arithmetic progression. Here you fix a number h, and then you take its translations, h to h, 3h, and then you can show that eventually it will be close to f. Not only that, but you can also show that a positive proportion of the elements from this arithmetic progression will be close to your target function f. And to prove this, it's like the first step of the universality, as I exhibited before, doesn't change at all. The logarithms should still be, of the twisted finite Euler products should still be dense in this space H omega, but then you have to change what approximates the twisted logarithm of the zeta m. In this case, you don't have tau, you don't have a continuous variable tau, but you have a discrete thing. In the case of Reich, it was an arithmetic progression, but you can have any sequence. And you need to prove this for a positive proportion of n. That's a must. And the second one is to show that the logarithm of this find Euler product is close to the logarithm of the Riemann zeta-function on this sequence, which is actually a very difficult problem when Hn is not an arithmetic progression, because when it's an arithmetic progression, it behaves more or less regular. Otherwise, you have many more problems, which I will show an example later on. So if you have all these three conditions, then you can get discrete universality with respect to the sequence Xn. So to show this, you just use something which probably all of us know. It's the pigeonhole principle. This is how everything starts, that you have n plus 1 objects, and at least one of these boxes should have at least 2 elements. And this has been used by Dirichlet to show that any rational number can be approximated by rationals with a certain degree of error. This idea has been improved later by Kronecker, who showed that if alpha is an irrational number, then the fractional parts of n times alpha, as n runs from 1 to infinity, cover the unit interval. So it's dense in 0, 1. And this has been improved by Weil in the 1920s, where he developed his strong theory of uniformly distributed sequences. And in this case, it says for the Kronecker sequence, which is this n alpha, there shouldn't be dots here anyway, so that not only the fractional parts are dense in the 0, 1 interval, but each subinterval of the 0, 1 interval have their fair share of elements as n goes to infinity. When I say fair share, that this proportion should be equal to the length of the interval. Weil also has generalized this concept to the multidimensional case, and we say that a sequence a alpha 1 time, you have a tuple in the Rn of alpha 1 times no times, comma alpha n times some real numbers xn. We say that this is uniformly distributed modulo 1. If for every box in the n-dimensional unit cube, we have that this fair proportion of fractional parts of each coordinate on the box. It should be equal to the volume of the box. And using this, we can show the second step of universality, namely that the logarithms of the finite Euler products are close to some twist. Now, the thing is that there is a connection with linear dynamics. And as I said, I started my first talk talking about operators and Birkhoff operators, which are translation operators. And now I have shown you that there is a wide family of zeta and L functions which can be hypercyclic vectors. So what I mean, I will do a small recap. We have some Fréchet space or a Banach space if you prefer, and you have an operator on this space, which is continuous and linear. That's the definition of an operator in this case. And you also have a family of operators, which is called cdot semigroup, and has these properties that the T naught is the identity operator. The composition of two operators should give you the operator with index tau plus rho, and also that the operator converges in a certain sense in a limit to tau with index rho when tau goes to rho. Now we say that a vector is a hypercyclic for one operator, in this case T, if this limit is positive, namely that for every open set of the space X, the orbit of the vector X under the operator T intersects U frequently often. And the second line is the continuous analog. Instead of having the orbit under the operator T, you have the orbit of X under the continuous family calligraphic T. And as I said, Voronin's theorem shows that the logarithm of the Riemann zeta-function is a frequently hypercyclic vector for the family of translation operators which shift vertically the argument of your target function f, while Reich's discrete analog of Voronin's theorem shows that the logarithm is frequently hypercyclic for each individual operator when you take its iterations with a composition. So the same you can show that it holds for the Hurwitz function, any other Dirichlet as L or zeta L function, which you know continuous universality and discrete universality. Now, there is a connection between continuous and discrete, and this is also visible to the linear dynamic sense. So you can see immediately by definitions that if a vector is frequently hypercyclic for one operator of the family, then it's also frequently hypercyclic for the whole family. This needs a small continuity argument, but it's not difficult to see. The more difficult case is the converse part, showing that if it's frequently hypercyclic for the continuous family, then you can go back to arithmetic progressions. Namely, you can show that the vector is hypercyclic for each operator of the family under composition of itself with itself n times. And this has been done recently like almost 17 years ago by Conejero, Mula, and Peris. This is something in functional analysis. And this has applications in the universality of zeta functions. So you can see immediately that the strong universality of the discrete universality of the Hurwitz zeta function are equivalent because of this statement above. Now, I haven't been honest through the whole talk about the logarithm of Riemann zeta function. I was using very easygoing. So one could say that you can do that also for the logarithm of the Riemann zeta function, because it's also strongly, the logarithm is strongly universal and continuous and discrete. But in this case, the vector x has to be vector of the space x, to use this theorem of Conejero, Mula, and Peris. But the logarithm of the Riemann zeta function, we don't know whether it's analytic in the strip of complex numbers with real part between 1/2 and 1, or equivalently, we don't know if the Riemann hypothesis is true. So how do we work with the logarithm then? I mean, I was using the logarithm all the time, right? So if I have zeros inside the strip, hypothetical, which we don't know, how can we do things unconditionally? The thing is that you use zero density estimates. So you have this complex plane, and you have that the logarithm, let's see, can I write here? So you have that the logarithm of zeta of s is okay when you are on the right of 1, because there are no zeros for the Riemann zeta function. It's an analytic function, no problem. So what happens if there is a zero of the critical line somewhere here? So maybe somewhere here. What you do if there is a zero, you remove this segment. Then you go to the next zero, which could be here. I don't know. And then you remove this segment. Of course, it has to be straight. My handwriting is not perfect. The thing is that as you go higher, because you use zero density estimates, these cuts become more sparse. So it may happen that you have a zero then here, and you take out this, but the next one should be even further. It cannot be even visible. So it so happens that if you have a compact set with compact set K, and you want to approximate a function on the set K, you cannot approximate it on this height, obviously, with a logarithm, because it's not an analytic function. However, when you shift the set K sufficiently high, it will be in this slit half plane without these vertical cuts. And then you can use the techniques that have been developed by Voronin to approximate with the logarithm, which is an analytic function when you remove these cuts. Yes. So another thing of discrete universality, which is not which does not follow from functional analysis, is when you have shifts coming from monomials and the exponent alpha here is not 1. If it was 1, you have an arithmetic progression, and there is this connection between operators and families of operators. But what happens when you have such a power which is not 1? The thing is that the second step of universality is easy to obtain because it is based in this Veil's multidimensional theorem of uniform distribution sequence of uniform distributed multidimensional sequences. And indeed, you have any collection of primes, and you take the logarithms, then this multidimensional sequence, it was already known by Veil that it is uniform distributed modulo 1. No problem there. The problem is the third step. You want to approximate in the mean square the logarithm of the Riemann zeta function by the logarithm of family products along these monomials. And if it's not an arithmetic progressions, you want to approximate this quantity and to be quite small when you have more terms. And this boils down to estimating these expressions. These are called exponential sums. It would be an overstatement to say how important they are in analytic number theory and how difficult it is actually to estimate them, especially when alpha is not 1. It's anyone's game. So this is really hard to estimate. However, you can say, okay, if I cannot do it for explicit alpha, for explicit beta coefficient, can I do it on average for most beta? And there are mean value estimates of exponential sums, which show that this quantity here, this exponential sum, can be small on average for almost all beta. And then you can use this property to show that this approximation is small for almost all beta, and thus this universality theorem can be also attained for almost all beta. Not an explicit beta like beta equal to 1, but almost all beta. And the third kind of universality, moving away from discrete universality, is now the conductor aspect universality. So as I said, in the second step of universality, in the first step, you had certain twists that approximate your target function, but then you need to change from the twists, which are multiplied by these complex numbers of the unit circle, to primes to the power of I tau as tau goes to infinity, or IHN as n goes to infinity, or if you have L functions without an only product, by the frequencies L lambda n to the I tau. And you want to have some sort of independence, or they behave randomly, which happens for the primes and for under assumption that the lambda n's, the frequencies are linearly dependent over the rational numbers. However, you can do something different. Instead of fixing a zeta or an L function and going high, so your tau, your tau, and then you hope that P of I tau for some tau will be close to this twist. What you want to do is to increase the family of L functions you consider. So instead of having one function, at time 10, you have 10 L functions. At time 100, you have 100 L functions, but you don't shift their argument. You just increase the family of L functions. And you hope that as you increase the family, one of them should be close to your target function f. And this is exactly what I write here. So you just have some increasing family, lambda q, of functions having a certain property, and then you hope that this limit exists and is positive. In this case, exactly, we don't approximate the twist by p to the I tau for sufficiently large tau, but e to the argument of the complex number a times a of p, but this a changes as time passes. It's not, but it corresponds to a collection of L functions. And if you have this, then you can prove and it's called the universality in the level aspect or in the conductor aspect. It's similar. So the first example was again done by Bakci in the 1980s. You have a collection of Dirichlet functions of modulo a prime number, and you take this collection for every prime. You just send prime to infinity, and this family of course increases because there are 5p main characters modulo p, which are in this case is pi minus 1, and he could show that this limit existence is positive. And the key element in our case, we had to use in the continuous universality, we had to use that a sequence is uniformly distributed modulo 1. In this case, you need to show that the more characters you add, which are numbers in the unit circle, at time p, you add more points in the unit circle. These points should be uniformly distributed in the unit circle on a certain sense. Sorry, I just saw the question. I will actually I will finish shortly, and I will check it out right away. And so you have this sort of independence over the coefficients of this family, and this is for all characters modulo P, but you can also do it for any collection actually of characters which have some sort of independence. And for this classical example by Misu and Nagosi, you just have all square-free integers D, which are congruent modulo congruent R modulo 8, and then you take the characters which are given by the Kronecker symbol, and you can show that this collection is universal, meaning that this limit exists and is positive. And these are all L functions with respect to Dirichlet functions, the easiest case, and corresponds to functions which have degree 1, as they are called. But there are also functions of a certain degree, higher degree, which are also in the level aspect universal. And in this case, it's the recent result by Kowalski in 2017. So you have, if you fix a prime Q, and then you take the increasing family S2Q, which is its set consists of the primitive cusp forms as modular forms, as I said before in definition, of the Hecke subgroup gamma naught of N. This is just a subset of it's a subgroup of the full modular group of PSL to Z, where the third entry C is congruent to 0 modulo N. And weight 2, the weight was defined, as I said before, for the modular form. And you have the associated L function. How? You have this Fourier expansion of the modular form. You take the coefficients, the Fourier series, from the Fourier series, and then you construct the Dirichlet L function. And this family of L functions, as you increase Q being prime, is also universal. And in this case, you need, again, something like that. An equidistribution theorem on the unit circle, and in this case called a local spectral distribution theorem. And this has also been done as in a variant of Kowalski's result, also for Hecke mass forms. So you have a Uj to be an orthonormal base of the space of Hecke mass cusp forms from PSL to the modular group. And you construct the associated Dirichlet function. And these coefficients are actually the eigenvalues of this equation. Here, T, P are the Hecke operators, and Uj is from your basis. And you can show that a positive proportion of this function can approximate your eigenfunction F, where the sense of positive proportion is with respect to the Laplace eigenvalues. This is also something which connect to Hecke mass cusp forms. And again, you just need an equidistribution in the unit circle, or actually in a certain product space. And this takes the form of Sarnak's equidistribution theorem for Hecke eigenvalues. And these are all the kinds of the known kinds of universality. And I think I will conclude here.
Thank you very much.
Let me.
Please go.
Only I need to check the question I had.
Let me stop recording.